Welcome to Electronics Pariksha channel. Today we'll solve some more problems of diode circuits, analog electronics. Today we have a couple of problems which are very important with respect to GATE and IES examination. These questions are asked in previous GATE and IES examination, and also there is a possibility for these questions to repeat in the future examinations. Okay, GATE, IES, ISRO, DRDO, any competitive examinations, these questions will definitely support you. Now we'll try to solve these questions in great detail. Now we'll see the first question. A voltage of 1000 sine omega t is applied across the terminals YZ. Assuming the diodes are ideal, the voltage measured across Wx in volts is. So he is asking us to find out the voltage across this X and W. This is a W and this is X across these terminals, and input voltage is applied between Y and Z. That is a sinusoidal waveform of 1000 volts peak voltage. Okay, now if we observe carefully, during the positive half cycle, this is positive and this is negative. If you observe carefully, during the positive half cycle, diodes will be reverse biased. Diode D1 and D2, N type is connected to positive terminal, and diode D3 and D4, P type is connected to negative terminal of the input voltage. So all the diodes will be reverse biased during the positive half cycle of input voltage. All diodes will be reverse biased, so there won't be any current flow. Output will be 0. The output voltage will be 0 volts. So what happens during the negative half cycle? During the negative half cycle, if you observe the circuit, this is the circuit. Diode D1 and D2, these are connected to D3 and D4. So this is the input voltage here. Here input is given and output is collected across this resistor. Here W and X. So during the negative half cycle, this is usually negative and this is positive. So D1 N type and D2 N type is connected to negative terminal of the input voltage, and P type of D3 and D4 connected to positive terminal. So all diodes will be forward biased. During the negative half cycle, all diodes will be forward biased. So diodes do conduct and they act like a short circuit because these are ideal diodes. All diodes act like a short circuit. So now we'll replace these diodes with short circuit, like closed switch. All diodes act like a closed switch because they are in conduction state. So closed switch is nothing but indirectly, in other terminology, it is like a short circuit. Now, what will be the output voltage? The current flow through the diodes only. There won't be any current flow across this resistor because the short circuit, this closed switch of the diodes will offer low resistance compared to this path. So W and X, the output voltage, is taken across short circuit, which is usually 0 volts. So the output remains 0 volts for all values of input voltage, all values of applied input voltage. Okay, answer is option D. Here the output is 0 because W and X are collecting the voltage across this short circuit. So the voltage across short circuit is 0 volts. So the answer is option D. We'll see the next question. Like the video, share the video, and subscribe to the channel for better content and more videos. Next question. In the following limiter circuit, an input voltage Vi is equals to 10 sine 100 pi t is applied. Assume that the diode drop is 0.7 volts. So he's telling that the diode drop is 0.7 volts here, D1 diode. When it is forward biased, the Zener breakdown voltage is 6.8 volts. So he's giving the Zener voltage is 6.8 volts. What are the minimum and maximum and minimum values of output voltage? It's very fine. So we have to take two cases, during the positive half cycle and during the negative half cycle. This is diode D1 and this is Zener diode D2. Sorry, Zener diode, and there is another diode D2. This is D1, this is D2. So during the positive half cycle, the input peak voltage is 10 volts. So during the positive half cycle, diode D1 is forward biased, and D2, which has a cutoff of Zener voltage, breakdown voltage of 6.8, enters the breakdown region and current flows in this branch. So the voltage drop across D1 is zero point 0.7 volts, and voltage drop across VZ Zener diode Z is VZ, that is 6.8 volts. And what is the condition of D2? D2 is reverse biased here. So it acts like an open switch. We'll replace this with open switch. It acts like an open switch. D1 acts like a closed switch. Now what is the output voltage here in this case? The output voltage will be VD1 plus VZ. That is the output voltage. So output voltage is nothing but VD1 is 0 0.7 volts plus VZ is 6.8 volts. So it will be 7.5 volts. This is during the positive half cycle. During the positive half cycle. During the negative half cycle of input voltage, what happens? During the negative half cycle of the input voltage, here diode D1 acts like an open switch, and Zener diode, even that is forward biased. Zener diode will be forward biased, but current doesn't flow through Zener diode because diode D1 is open. There is no current through the branch. So input will be minus 10 volt during the negative half cycle. So this is minus and this is plus. Zener diode will be forward biased, but D1 is reverse biased. Here diode D1 will be reverse biased, acts like a open switch. So there won't be any current flow through the Zener diode. And the current flows in this direction through D2. And D2, the voltage drop across D2 is 0.7 volts. So the output voltage here is VD2 minus VG2 because it is in reverse direction. So it is minus 0.7 volt. Okay. So during the negative half cycle, it is minus 0.7. During the positive half cycle, it is 7.5. So answer is option C. These are the maximum and minimum voltages at the output. We'll see the next problem. For the Zener diode in the figure, the Zener voltage at NIC is 7 volts. Means he is telling the Zener voltage VZ is equals to 7 volt. That is breakdown voltage of Zener diode. Next, the knee current is negligible and the Zener dynamic resistance is 10 ohms and the input voltage ranges from 10 to 16 volt. Okay, input voltage ranges from 10 to 16 volts. He is telling Zener diode has a dynamic resistance. Here there will be resistance component that is 10 ohms. The output voltage ranges from. Okay, we'll see here. This will be the actual circuit. See, this is 200 ohms is the series resistance, and there will be Zener resistance RZ, which is equal to 10 ohm, and a Zener diode whose drop will be 7 volts. Sorry, this is positive and this is negative. This is 7 volts drop. The input voltage is applied here, V in, which is ranging from 10 volt to 16 volt. Output voltage is collected here. So he's asking V out minimum, V out range, V out minimum, and V out maximum. Okay. Now we'll see what is V out. The output voltage is nothing but VZ, that is the Zener voltage, 7 volts, plus the voltage across this Zener resistance also. This Zener 10 ohm resistance. So that is equals to RZ into I. Output voltage V0 is equals to Zener voltage is 7 volts. RZ is 10 ohms. What is I? I can be written like this. The formula for current flowing through Zener, that is Zener diode, is V in minimum minus VZ divided by series resistance RS. This is the well-known formula for us. Okay. So V in minimum is nothing but 10 volts. VZ is 7 volts. RS is 200 ohms. But here, one more important thing is, here RS plus RF we have to take. RS plus RZ. Because current is flowing in this direction. So current is seeing the resistances, series resistance 200 and the Zener resistance 10 ohms. So it will be 210. Hope this is clear. 210 ohms. So output voltage V0 is equals to 7 plus 10 minus 7 is 3 divided by 21. So the output voltage 7 plus 3 3 by 21 is equals to 7.14 volts. This is V out minimum because we have considered V in minimum voltage. Next, we will consider V in maximum voltage. Second case. Okay, this is V out minimum. For V out maximum, we have to consider same formula Vz plus Rz into I, whereas I needs to be written like this. I is nothing but V in maximum minus Vz divided by Rs plus Rz, which is equals to 7 plus 10. V in maximum is 16 volts. V in maximum is 16 volts minus 7 volts divided by 210, which will be equal to 7.42 volts. So output ranges from 7.4 volts to 7.14. So the answer is option C. This question is asked in GATE 2019 and GATE 2007 also as well. We'll see the next question. The correct full wave rectifier circuit is, the correct full wave rectifier bridge circuit he is asking. So the bridge circuit is like this. This is primary winding and this is secondary winding. We know very well that bridge circuit contains four diodes: diode D1, D2, D3, and D4. Okay, this is D1, D2, D3, and D4. Output is collected at the other terminals of the diagonal. This is output load resistance. This is the full wave bridge circuit. This is input. So it contains four diodes. These are some of the important points of full wave bridge rectifier. Okay. For bridge rectifier, these points are very important. The output will be like this. The input contains positive and negative half cycles, whereas the output contains only the pulsating positive half cycles. The output frequency is 2 times that of input frequency. The output frequency is 2 times that of input frequency. And the output voltage, average output voltage, is equals to 2 Vm by pi. If you consider the voltage drop across diodes, it is minus 2 Vd. Vd is the forward voltage drop across diode, which is equals to 0.7 volts for silicon, 0.3 volts for germanium. Okay. The output average current will be 2 Im by pi. The output current RMS value will be Im by root 2. So if you take the form factor, these values are very important for examination perspective. Okay, form factor is nothing but VRMS divided by output VRMS divided by output average voltage. That is Vm by root 2 divided by Vm by 2 Vm by pi. Vm by root 2 divided by 2 Vm by pi, which is equals to 1.11. This is the form factor, very important value. This is very important, asked in various examinations like RRB, SSC, JE also. Next comes the transformer utilization factor. This is also very important. The transformer utilization for the bridge rectifier is 0.812. The efficiency, next comes the efficiency. Eta is equals to 81.2%. Even this is very, very important. Next, the ripple factor. Ripple factor for full wave rectifier. Eta is equals to 0.482. These are all the important values which are asked in various examinations. Even these formulas are very important for solving various problems. Okay, so what is the matching circuit now? The answer is option C. C matches. The circuit C matches the bridge full wave rectifier. Now we'll see the next problem. For the circuit below, assume the Zener diode is ideal. He is telling Zener diode is ideal. Means the forward voltage drop across Zener diode is 0 with a breakdown of 6 volts. Okay, Zener breakdown voltage is 6 volts. Okay, breakdown voltage is 6 volts. Forward voltage drop, when the current is flow, when the diode is forward biased, forward voltage drop will be 0. Okay, the waveform observed across R is. So he has given the circuit. Input is 12 sine omega t. This value is very important because the diode cutoff voltage is 6 volts. If the input voltage is greater than this 6 volts, diode conducts. If the input voltage is less than 6 volts, diode does not conduct. That is the concept. Okay. So if during the positive half cycle, during the positive half cycle, if input voltage is greater than 6 volts, diode conduct. Diode enters the breakdown region and conducts. Current flows through resistance. Through resistance. So there will be output voltage drop. V out exists. If the input voltage is, if input voltage is less than 6 volts, current does not flow through the circuit and output voltage will be 0. Here we need to correct one sentence. If input voltage is between 0 and 6 volts, the output will be 0. Okay, because we are talking about the positive half cycle only, not negative half cycle. So waveform will be like this. This is the input positive half cycle, okay, whose peak value is 12 volts. This is 6 volts, Zener breakdown voltage. The output voltage will be here. So as long as the input is less than 6 volts, means this particular portion, as long as input is less than 6 volts, the output will be 0. Diode does not conduct. Once the input voltage crosses 6 volts, the output follows the input voltage. Okay, the peak value will be 6 volt only, and even this portion will be 0 volts. Okay, this is during the positive half cycle. During the negative half cycle, what happens? During negative half cycle, the diode is in forward biased mode. See, negative half cycle means it will be like this. The diode is in the forward biased mode. So current flows in this direction. And the voltage drop across diode is 0 because it is ideal diode. So during the negative half cycle, entire input voltage will appear at the resistance. So at the output voltage. So during the negative half cycle of the input voltage, the output is exactly as input, which is equals to, whose peak value is equal to minus 12, because input also it is minus 12. There won't be any voltage drop across the Zener diode, and Zener diode conducts because of forward bias mode. Okay, so the answer is now option B. Like the video, share the video, and subscribe to the channel for better content and more videos. Now we'll solve the next question. The Zener diode in the regulator circuit shown in the figure has a Zener voltage of 5.8 volts. Cutoff voltage is, the Zener breakdown voltage is 5.8, and the Zener knee current. So Zener knee current means he's giving IZ minimum. Knee current is 0.5 milliamps. The maximum load current drawn from the circuit ensuring the proper functioning over the input voltage ranges between 20 and 30 volts is. So the input is varying between 20 and 30 volts, and IZ minimum is given as 0.5 milliamps. He's asking maximum load current, IL max. So we have the formula I is equals to, can be written, the I is nothing but the series current here. This is I, series current, IS, which is equals to I. This series current will divide into IZ and IL. Okay, so we have the formula I is equals to IZ plus IL. This can be written in two parts. I remains constant, and IZ minimum. So if Zener current is minimum, load current becomes maximum. Similarly, IZ maximum. If Zener current is maximum, load current becomes minimum. These are the two formulas that we have. Okay, this is formula 1 and this is formula 2. But in both cases, I remains constant most of the time. So now which one we have to consider today? Because they have given IZ minimum and asking for IL maximum. We have to consider this formula. So writing down this formula, we have current I is equals to IZ minimum plus IL maximum. So I can be written like this, that is input voltage. This is the input voltage, and this is the Zener voltage in this branch. So input voltage minus Zener voltage. Here we have to take input voltage minimum. Okay, input voltage minimum minus Vz divided by resistance R, series resistance R, is equals to IZ minimum plus IL maximum. Now input voltage minimum is 20 volts minus Zener voltage is 5.8 volts divided by resistance 1 kilo ohm, that is 1 into 10 to the power of 3. IZ minimum is 0.5 milliamps plus IL maximum. By solving this, we'll get maximum load current as 13.7 milliamps. Okay, that is answer. So answer is option C. See here, you may get a doubt. Why only 20 volts? Input voltage, why we have to consider 20 volts? Why not 30 volts? See here, this is very important. Input voltage is changing. If you understand the Zener diode regulator concept clearly, you will not get this doubt. When input voltage is 20 volts, what is the load current maximum that we have to calculate? Means the load current will be fixed most of the time. If input voltage is 30, the current will be more than this 13.7. It will be greater than this 13.7 milliamps. Then where will go that extra current? That extra current will be drawn by Zener diode. So it will not enter the load. It will enter the Zener diode. That's why we have calculated with V in minimum voltage. If we calculate with 30 minus 5.8 divided by 1 kilo ohm resistor, it will be something like 24.2 milliamps. But the difference, the 24.2 milliamps minus 13.7 milliamps, the difference current will enter as IZ only. It will go to the Zener diode. It will not go to the load, not load. That's why we are considering minimum voltage. Always consider minimum voltage for calculating maximum load current. If you take this maximum value 30 volts as input voltage, you will end up taking the wrong answer. This is wrong answer, 24.2. You cannot choose that because the difference current will enter the Zener diode. It will not enter the load. Okay. Hope this is clear. We'll solve the next question. In the voltage regulator shown in the figure, the load current can vary from 100 milliamps to 500 milliamps. Okay, he's telling load current varies from 100 milliamps to 500 milliamps. Assuming that the Zener diode is ideal, the Zener current, D current is negligibly small. So he's telling IZ minimum is negligibly small, means he's telling it is 0 milliamps. The resistance is 0. Okay, there is no Zener resistance. So forward voltage drop across the Zener diode also mostly it will be 0. The value of R is, he's asking for the value series resistance. R is equals to, we know the formula, V in minus. Here there is no range for the input voltage. So I'm taking only V in directly, not V in max or V in minimum or V in maximum because input voltage is constant. V in minus Vz divided by series current IS. Okay. Then what is, we know V in voltage, input voltage is 12 volts. Vz is 5 volt. Then what is the unknown parameter IS? IS can be written as IZ minimum plus IL maximum. Minimum current of the Zener diode is 0. IL maximum is 500 milliamps. So IS is equals to 500 milliamps. Substitute here. R is equals to 12 minus 5 divided by 500 milliamps, which is equals to 14 ohms. So the answer is option D. We'll see the next question. The output voltage of the regulated power supply in the figure is. Here, the op-amp regulated circuit is given. We have to take the two principles of op-amp. Two principles of op-amp circuit here. First one is op-amp has infinite input impedance. Okay. Because of that, the input current in two terminals will be 0. Second thing, the voltage at two terminals, two input terminals of op-amp will be same, of operational amplifier will be equal. This is called virtual short principle. Will be same or equal. Okay. So whatever the voltage that appears at this terminal, at this positive terminal, same voltage will be there at the negative terminal also. That is called virtual short principle. So now if you observe carefully, at the positive terminal of the op-amp voltage, it is 3 volts. So at the negative terminal of the op-amp should be 3 volts. 3 volts only. There will not be the voltage difference between these two terminals. So the voltage across this 20 ohm resistor is 3 volts. That is known from this diagram. So the voltage across this 20 kilo ohm is nothing but 3 volts. So the current flowing will be, the current flowing in this 20 kilo ohm resistor is 3 divided by 20 kilo ohms. Okay. So same current. Now the input, we have understood that the input current of the operation amplifier is 0 amps. So the current will be entering like this. and it will go to this 20 kilo ohm. The input current for this operational amplifier will be 0. So current will flow in this direction only. So whatever the current that is flowing through 20 kilo ohm resistor will be same as the current that is flowing through 40 kilo ohm resistor. So now voltage across 40 kilo ohm resistor is current multiplied by 40k, like whereas current is nothing but 3 by 20k multiplied by 40k, which is equals to 6 volts. Okay, so the output voltage, if you see here, the output voltage will be the voltage across 40 kilo ohm resistor plus voltage across 20 kilo ohm resistor, which is nothing but 6 plus 3, that is equal to 9 volt. So the answer is option C. We'll see the next question. The DC power supply has no load voltage of 30 volt and full load voltage of 25 volt. At full load, the current is 1 ampere. Its output resistance and the load regulation respectively. The load regulation formula, that is nothing but voltage regulation formula, is in percentage is no load voltage minus full load voltage divided by full load voltage multiplied by 100. What is the no load voltage? It is 30 volts. Full load voltage is 25 volts divided by full load voltage multiplied by 100, which is equals to 20%. This is the voltage regulation. So he's asking the output resistance. The output resistance is nothing but the no load voltage minus full load voltage divided by the DC current. That is 30 minus 25 divided by 1 ampere, which is equals to 5 ohm. So the answer is option A. We'll see the next problem. For the full wave rectification, a 4 diode bridge rectifier is claimed to have following advantages over 2 diode circuit. He's asking the differences between, means advantages of a bridge rectifier over center tap. We'll see just the differences between bridge rectifier and center tap. Okay. If you see, center tap has 2 diodes. Bridge rectifier has 4 diodes. The transformer utilization factor of the center tap is 0.68, whereas for bridge rectifier it is 0.812. Okay, this is higher. Center tap uses center tap transformer, whereas bridge uses simple transformer. We'll see less expensive transformer. Yes, this is true. Smaller size transformer. Yes, this is true, because the bridge rectifier requires a simple, small, and less expensive transformer, whereas center tap is more expensive. This is more expensive. Next, suitability for high voltage applications. Yes, bridge rectifier is suitable for high voltage applications, because it is not suitable for low voltage applications, because the diodes, 2 diodes will be conducting at a time during the positive half cycle and negative half cycle. 2 diodes will conduct, so voltage drop will be 1.4 volt for 2 diodes. So if input voltage is higher, it is suitable, it is better for the bridge rectifier, because 1.4 volts will be negligible. If input voltage is in the range of 100 volts, this 1.4 voltage drop across the diode will be negligible. That's why it is suitable for high voltage applications. So answer is option D. Next question. The small signal AC operation, a practical forward bias diode can be modeled as. For a small signal operation, the practical diode can be replaced with a small forward resistance, because small signal operation, in the sense, if you see the diode characteristics, it will be like this. This is the cut-in voltage of the diode. V gamma is equal to 0.7 volt. So the small signal operation, this is a small signal state. The diode current will be usually very, very small, means the diode offers usually the forward resistance. As the current goes up, the forward resistance decreases. So this is a small signal operation. It can be replaced with a simple resistance. Whereas in the linear region, this particular region, you can replace the diode with a resistor as well as capacitor also, because forward capacitance will come into the picture, dynamic capacitance. We'll see the next question. The wave shape of the output in the figure is. So if you see, during the positive half cycle, Zener diode D1, that is 4.1 volt, will be forward biased, and D2. D2 is a conductor in reverse direction. So, for the current to flow during the positive half cycle, the input voltage must be greater than the forward voltage drop across this. We'll neglect the forward voltage drop. We'll consider only the reverse voltage. So, input voltage must be greater than 4.1 volt because this diode D2, Zener diode D2, should enter the breakdown region for the current to flow. So if input voltage is greater than 4.4 volt, only then the current flows. Otherwise, current does not flow. So the output remains 0 till input reaches 4.1 volt. Once input crosses 4.1 volt, output will be there. Similarly, when it touches below the 4.1 volt, it does not conduct. Okay. So this is the input half cycle. This is the output half cycle. This is 4.1 volt breakdown result. Okay. During the positive half cycle, if input voltage is greater than 4.1 volt, both the diodes conduct. Diodes conduct and current flows. Output exists. Similarly, for the negative half cycle, negative means this is negative and this is positive. For D1 to enter the breakdown region, D1 is reverse biased, D2 is forward biased. For D1 to enter the breakdown region, the input voltage in the negative half cycle must be lesser than minus 4.1 volt. Okay, this is the negative half cycle of the input voltage. So minus 4.1 will be here somewhere. So in this particular portion only the current flows. This one. I'll draw the clear diagram here. This is the input voltage and this will be the output voltage. Here input voltage, this is plus 4.1, this is minus 4.1. So as long as input is less than plus 4.1 for the positive cycle, the output will be 0. So when input crosses 4.1 volts, output exists. Similarly, for the negative half cycle also, as input goes less than 4.1, output exists. Otherwise, output will be 0. So what is the peak value of this output voltages? The voltage drop across these diodes will be 4.1 volt only. The forward voltage drop across the second diode is negligible. So the remaining voltage will be here at output. It is 5.9 volt. So it is 5.9 plus 5.9 minus 5.9. So the answer is option B. The remaining options are not shown here. We'll see the next problem. The diode in the circuit has V on, that is the diode forward voltage drop as 0.7 volts, but ideal otherwise. If the V input is 5 sin omega t, here sinusoidal waveform is given whose peak value is 5 volt. Now the minimum and maximum values of output voltage are. So he is asking the minimum and maximum values of output voltage. V out minimum and V in minimum. V out maximum and V in minimum. We'll calculate what is the V out. So here if you analyze, the diode is in forward biased, so current flows like this. During the positive half cycle, the diode is forward biased. During the negative half cycle, the diode is reverse biased. During positive half cycle, diode conducts. Diode is in forward biased, so conducts. So the current flows in the circuit. The output voltage will be the current that is flowing through resistance R2 plus diode voltage drop VD plus 2 volts. The current that is flowing in the circuit is V input voltage, that V input voltage minus 2 volts divided by total resistance R1 plus R2. Here the forward voltage drop also should be taken care, minus 0.7 also, plus 0.7 diode voltage plus 2 volts. So if you substitute the values, input voltage is 5 minus 2 minus 0.7 divided by R1 plus R2 is 2 kilo ohm plus 0.7 plus 2, which is equals to 3.85. This is during positive half cycle. During the negative half cycle, Diode D will be reverse biased, so it does not conduct. Acts as an open switch. So output is nothing but input voltage, that is minus 5 volt. During the negative off cycle, input will be minus 5 volt. So the answer is option C. Sri Raghava Academy online coaching center for the regular and backlog students dedicated to diploma and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.